So welcome everyone to Financial Mathematics. In this course, we will use a probabilistic approach to model financial assets, financial products. This course is a companion course of computational finance in which you will see the numerical techniques for modeling, for example, a European call, a European put, an American option, Asian options, barrier options, and so on. So in this course, what is important to understand is that we use a probabilistic approach, which is one of the different theoretical approach we can actually use to model a financial asset. Now, in doing that, and in order to successfully treat all the topics, and there are many topics that we are going to see together, and I'm thinking about the fundamental theorems of asset pricing, naturally Black-Scholes, and the implications of Black-Scholes, the different type of options we will consider together, and a little bit of fixed income. Okay, to deal with all those topics, we need some instruments. Now, what I will do now is to start in the first classes to build the basic knowledge that we need for reaching our goals. But as you will see, this is not at all basic knowledge. So there will be a lot of knowledge that I take for granted. So we are at a master level in mathematics, so it's obvious that I assume you know already many things. For example, I will assume you are familiar with the Brownian motion. I will assume that you are familiar with the concept of martingale, and I will assume that you are familiar with all the basic probabilistic machinery. I will not spend time, for example, in introducing the Brownian motion, and I will assume you know what is the quadratic variation of the Brownian motion, or the fact that a Brownian motion is not a bounded variation function on, for example, a given time interval. So it's very important that if you are not familiar with that, or you do not recall some of those topics, you activate immediately and you look for resources. On Brightspace, you find some suggestions, but it's very important that you are understanding what I'm saying, because it's very easy to get lost if you start missing the first parts of the course. Conversely, I will not assume that you are familiar with stochastic calculus, and in particular with the Ito integral and the Ito formula. These are topics that we will cover together. And as well as other topics in probability, like the change of measure, the implications of the change of measure, because they have very important financial interpretations. So it's very important that even if I'm sure you saw the change of measure before, you understand what is the meaning of a change of measure in a financial context. So let's start with our course. So the topic of today is essentially the introduction of the Ito integral, and we will try to see how actually Ito approached this problem. Now, let's see if we can understand why there is the necessity of introducing a new integral like the Ito1, and conversely, we cannot rely on the Riemann-Stieltjes integral that we all know very well from our courses in analysis, calculus, or whatever was the name of the courses you had in the past. Now imagine that we are considering a portfolio. We are considering a portfolio, and obviously the value of this portfolio changes over time. But at this very early stage, we assume that the portfolio is something deterministic, so there is no randomness in it. Now let's assume that with Pt, for t non-negative, being time, with Pt I indicate the value of the portfolio at time t. And I also make a further assumption to make things easy to start. I assume that my portfolio is a portfolio that just depends on interest rates. So it's a portfolio that contains assets like bonds that are linked to interest rates. And even more, I assume that the interest rates, the reference interest rate, the yield, whatever you want to call it, is 1, and again, it is deterministic. With RT, we indicate the instantaneous interest rate. Now, question that we can ask ourselves is, what is the possible variation of our portfolio over time? So what are the changes in the value of our portfolio? Since we are in the deterministic framework, answering is very simple. So we can simply consider an equation of this type. So we consider an infinitesimal time variation of our portfolio PT, and necessarily having the instantaneous interest rate and given all our assumptions about deterministic behavior and so on, this is just RT PT. Now, if we specify the functional formula RT and if we give more information about PT, this is nothing more than a differential equation that we all know how to treat. So this is nothing new. You can go back to your knowledge of differential equations from your courses in analysis, and you know how to play with this. But you know also very well that assuming everything deterministic, first is extremely boring, and second is not true. And third, okay, I'm professor in probability, so what would be my job if everything were deterministic? So what we will do now is to immediately drop this deterministic assumption. In dropping deterministic assumption, we can ask ourselves why we need to introduce randomness. Now, for sure, we know from the observation of the market that quantities like the value of a portfolio, like the behavior of interest rates, have some variations, some behaviors that for us are not immediate. It's not very simple to us to understand the mechanics behind these things. Now, there can be many different reasons for that, but if you want, we can, and I think actually it can be a very nice way of seeing this, we can use the approach of Laplace. So Laplace saw randomness as the result of incomplete information or as the result of constrained computational power. So the idea of Laplace is the following. It can be the case, and maybe it really is, actually it thought it was, it can be the case that quantities like RT, so the instantaneous interest rate over time, are deterministic. But since we have limited capabilities, maybe from a computational point of view, and we have limited access to information, for every single person in this room, it's impossible to have access to all the information in the world at a given time instant. It's something that is not possible. It is not possible even for Bill Gates or Bezos. It's not something that is just linked to the fact that we are not billionaires or that we are not the chiefs of fantastic, super huge international company. It's just the fact that this is not possible for the limits of our understanding and the limits of our knowledge acquisition. So because of this limitation, what happens? It happens like a veil between us and the truth, and between the true value, for example, of the interest rates and the dynamics of the true value appears. And this veil does not allow us to see through it completely, but it's just something that blurs the background. So maybe we can have some idea about what is gonna happen, but it's a blurred idea. So imagine, for example, that we are considering our interest rates and that the true interest rates is a deterministic function of this type. It means that with probability 1, this is the trajectory. So that's how it evolves. But then because of this sort of veil, because of our incomplete knowledge, we're not able to see this. It's like there is, again, a veil on top of that that blurs everything. And we discover that the interest rate will be somewhere around this true value that we cannot observe. Immediately, we cannot use this type of tools, but we will have to find tools that allows us to have functions that can be like this, can be like this, can be like this, can be like this, and so on, in order to be able to deal with this incomplete information and with this randomness that emerges from our observation of the world. Now, what we can do in order to reach the integral is to try to continue our discuss about the change in the portfolio by assuming that now the interest rate is no longer deterministic, but it has some random component. So let's assume that for me at time t, rt is equal to some value r, and we can assume r to be a constant. In principle, in many textbooks now, I would say are non-negative, but we know that in reality we can experience negative interest rates. And in this course, I will stress a lot what is the impact of a negative interest rate on several basic models that we will consider together, or in operations like the change of measure that guarantee risk neutrality. So, but for the moment, R is a constant. And we say that RT is equal to a constant plus another constant, call it A, that multiplies a quantity WT. What is WT? Since we want to introduce randomness, WT is nothing more than a stochastic process. What is a stochastic process? A stochastic process is a collection of random variables that is indexed by some mathematical set. Now, most of the time, this mathematical set of indices has a physical interpretation. So, for example, it can be time, and this time can be continuous or can be discrete, but there are situations in which obviously the indexing set has a spatial interpretation, a spatial temporal interpretation. Since we are very simple financial guys, for us, it will always be time, so we will not consider spatial processes. So for us, a stochastic process is nothing more than a collection of of random variables whose value obviously change with time. So we have different time points, and at every time point, we will have a random value associated to these random variables. Now you can imagine from what you know from stochastic processes that there are many stochastic processes that can be used. So we can think of the Brownian motion, we can think of the Poisson process, we can think of any type of semi-martingale, and many things. We can think of Levy processes. It's many possibilities. So what I suggest to do is to start from a class of processes which is simple and at the same time large enough and flexible enough. Which is to say, let's assume WT to be a so-called white noise. Now, I know that sometimes, especially in physics and other fields, white noise, or sometimes even not properly in statistics, white noise is used as a synonym of Brownian motion. Please, this is not the case. So white noise is a process that satisfies three different properties. The idea is that if I consider two time instants t and s, and assume that they are different, so for example, today and 10 days from now, then wt is independent from ws. So there is this temporal independence. The second property is what a statistician would call strong stationarity. You know that strong stationarity in time series is a requirement. Okay, is the strongest one, so obviously you can relax it in several ways, but it's for sure a condition for a time series to be predictable, to be easily treated and modeled. In practice, what do we require is that if we consider a certain number of time points, say t1, t2, up to value tk, and we take a constant h positive, then if we consider the finite dimensional distribution of our process W evaluated in the different time instants, that is to say WT1 up to WTK, strong stationarity requires that in distribution, this is the same law as the law of WT1 plus H and WTK plus H. What does it mean? It means that I have a certain window between T1 and Tk. I observe my process and its realizations. If, for whatever reason, I shift the window by a constant, like, for example, instead of considering what is happening between now and 10 days from now, I shift everything in 1 year from now, and I consider 10 days in 1 year from now. So if I do this shift, under strong stationarity, what I have is that the finite dimensional law of these is exactly the same as the finite dimensional law of this. So time shifting has no impact on the distributional property of our process. The third requirement for our process to be a white noise is then finally that for every t, Wt is such that the expectation of Wt is equal to 0. So this is important because we're saying that these random variables at any time point are just random variables with mean 0. For us, it makes sense because assume that we are really modeling the interest rate. We are saying that there is a value of the interest rate R, which is a sort of reference value. And then we have oscillations around this reference value given by these random variables that on average have mean 0, expectation 0. Now, if I assume this, and I assume that this is my white noise, what happens? I can immediately rewrite my equation here. So let me underline the equation. I can immediately rewrite this equation by substituting the functional form of R. So let's do that. It's just a simple substitution. So dt here, pt, and then we have RT, that now is this object, multiplying PT. So we have R PT plus A PT WT. Okay, now we could be inclined to think that we can still play with this differential equation, as we are used to do. Now, immediately, it should be clear that this is not true. So we cannot just apply the machinery we know from differential equations to this situation. Why? Because this guy here, this WT term, now is a stochastic process and is something that is random, that changes over time. So if we fix this value and we say that this value is 3, or we say that this is a deterministic function, like, I don't know, t squared, then we can still try to play with this object as an ordinary differential equation. But if that quantity is random, as it is, and it's a very general type of process, what we have is that for every single trajectory of WT, we have a different differential equation. This implies that we are dealing with a very tricky object that our standard machinery is not able to deal with. So we have to find alternatives. Now, one thing that we can try to do is to be able to still solve equations of this type. And one thing that my teachers, my professors in the past taught me is that you never have to be someone that wants to be immediately disruptive. So if you want to find a solution of a mathematical problem that for the moment has not been solved yet, it is not necessary to try to be disruptive from time zero. Most of the time, the solution can be found by starting from what you already know, and by trying to relax some assumptions, add some extra assumptions, and so on. In other situations, you really have to invent a new field of mathematics. But let's say that this is not the case for us. So one thing that we could do is to try to make an educated guess about the type of possible solution of an object of this kind. If this is the case, by recalling our results from calculus, what can we do? We can say that the possible solution is probably something of this type. It's Pt equal to some initial value, P0, plus R is a constant, so it's R, the integral between 0 and T of Ps ds, plus A, again a constant, the integral between 0 and T of Ps ws ds. Now, if I'm right and I have a look at this equation, I could say that I'm done, because I have a term P0 that makes sense and is not a big problem for us. We have a nice integral here that we know how to solve. Hopefully, obviously, everything depends on P, but we know how to do that. At least, even numerically, we know what we can do that if the analytical solution is not attainable. And then we have the last term. The last term is this term here. But again, we are in the same situation as before. Before we were playing with the differential equation, now we have the integral. But again, this integral is something that cannot be treated because of the irregularity of W in the common way. So it's not possible to treat this integral as a Riemann Stieltjes integral. Why? Because again, we have this object here, WS, that might have very erratic trajectories. And that makes the integration a problem. Now, a solution at this point can be the following. We could say, okay, let's stop here. There is nothing I can do, but this is not we mathematicians like to do. And what I can try to do is to find a solution by, for example, simplifying a little bit this object. The idea is that instead of starting from this very general process I'm defining here, that can be tricky. Why don't I play with a process that I know very well, that has a lot of nice properties that we have studied, that you have studied, and that we can essentially exploit in studying this integral. Quite natural solution then, if you think a little bit about all the processes you have studied, is to use the Brownian motion. So the Brownian motion is an object that, despite being able of very tricky behaviors, and it's a fascinating object because despite its simplicity, so it's not difficult to define a Brownian motion, but despite its simplicity, we know that the Brownian motion can have very surprising behaviors, sometimes not at all intuitive. So what happens? In any case, it's something that we have studied for years. We know how to play with it. At least in the univariate framework, I would say that we know 98% of what can be known about the Brownian motion. So let's try to use the Brownian motion. So an idea could be to substitute this term here, ws ds, with some dbs, where bs is a Brownian motion. So I try to substitute this integral here, rewriting it such that I'm not considering, okay, a, that is not important, it's just a constant, so it's out for us, 0 t ds, dbs. That is already an integral in the form of the Ito integral that you know at least once in your lifetime. You have already seen that. Now the point is that if I look at this integral and for a second I ignore the fact that this is a Brownian motion, I can think of, it's very simple. This is some sort of Stieltjes integral. So I'm just integrating with respect to a function, and that function is called the Brownian motion. Yes, okay, but if you recall the properties of the Brownian motion and what you have seen for sure in the course Brownian motion, Martingales, and friends, the Brownian motion has a problem, let's call it a problem, for the Stieltjes integral to be defined. Any clue? What do you know about the total variation of the Brownian motion? For example, I consider the Brownian motion, and I consider the Brownian motion of the interval 0t. What do I know about the behavior of that Brownian motion? The Brownian motion is not a bounded variation function on 0t. So immediately, this integral cannot be defined as a Stieltjes integral, as a Riemann Stieltjes integral. So even substituting this white noise in a way such that I can rewrite WSDS as dBs, so an infinitesimal increment of the Brownian motion, appears not to be the solution to be able to treat all these things in the usual way. And actually, there is no way, and that's to summarize, there is no way in which I can actually treat this type of objects in the usual way. And usual way I refer to the basic machinery we have from analysis and calculus. Why? Because not bounded variation, it's a very erratic object. Think about the increment of the Brownian motion. Now, think of the classical idea of the integral. What do you have when you take an integral, a Riemann Stieltjes integral? What are you doing? You have a function, then the integral is defined as the limit of the sum of all these rectangles that you use to approximate the function. Fine. And if you integrate with respect to another function that allows you still to play with the integral, like in the Stieltjes representation. What are you doing? Instead of integrating with respect to time, if we consider dt and t represents time, you are integrating with respect to some sort of modification of time. So instead of integrating with respect to the x-axis that contains time, you are now integrating about some sort of function that transforms time. But the rectangles idea still works. Now, the point here is that if you want to use the rectangle as idea, now what you should immediately observe is that here you have, in principle, rectangles whose width changes. So we have something that is extremely unstable and cannot be treated in the usual way. So the solution is to introduce a new definition of integral that allows us to play with objects of this type. Now, in the literature, there are different possibilities. There is Ito, there is Stratonovich, there is Fisk, and many other possibilities. What we will do here in this course is to follow the Ito approach. Not because the others are not interesting, but because for sure is the most used approach. For sure is the approach on the basis of which you perform all your approximations and discretization in computational finance. And it's the de facto standard for treating with stochastic processes, at least in finance. So what we are going to do now is to define the Ito integral. And we will try to do that from scratch.